it gives me great pleasure to introduce the first of our speakers, Professor Mini Saaj from the University of Lincoln. She is the Global Chair in Robotic Engineering there and lead for research in industrial digitalization and systems intelligence. Previously head of robotics and control and director of postgraduate research at the Surrey Space Centre. She is an expert in modeling control of spacecraft, design and control of manipulators, systems engineering using model-based systems engineering approaches. She has the Airbus RA Eng Secondment Award and the University of Surrey Vice Chancellor's Teaching Excellence Award. She is a chartered engineer and a senior member of the IEEE, the AIAA, and a member of the IEEE Women in Engineering. So it gives me great pleasure to introduce her to speak on robots and mathematics. Are they related? Mini.
Thank you very much, Richard. Good morning, all of you. Good afternoon or good evening, based on your current locations. I hope audience, all of you can hear me very well. Today, we are going to explore the elegant relation between mathematics and robots. So are you ready to take off? Well, before I kick off, let me say a few words about my university and my current activities. But let me start with the copyright and disclosure note, because I'm aware that IMA will be recording this presentation and will be publishing this more widely at the end of this series. So I would like to remind that there are materials which are copyright protected in this talk, but it's okay to publish provided the regulations are correctly followed. We are based in Lincolnshire, and the University of Lincoln is a public research university based in the East Midlands. We are rated one of the top 20 universities in the UK by the Guardian University Guide 2020. And we are also recognized as setting a blueprint for elegance in pioneering approach for working with industry. So University of Lincoln is very active in undertaking robotics and autonomous systems research, and it's a real honor to be part of this vibrant team. And today I'm going to talk about some of the robotics research I have been part of whilst I was working at University of Surrey previously, and also some of the new initiatives I'm leading at University of Lincoln. So University of Lincoln has multiple research activities connected with robotics, which are led by the university research groups and centers, and also institutes. For example, the Lincoln Center for Autonomous Systems is a cross-disciplinary research group run by the School of Computer Science and School of Engineering. As part of the Lincoln Center for Autonomous Systems, there are several research initiatives which focus on applications of robots and autonomous systems or AI-driven solutions for future generation of robots, which includes not only robotic manipulators, but also mobile vehicles. And we do cover a wide range of application sectors, ranging all the way from space down to earth, which covers agri-food, healthcare, digital aspects such as logistics, supply chain, the nuclear industry, human or the human-robot interaction aspects, and obviously a lot of application to transportation as well as the energy sector. So today I'm going to keep it more focused on some of the recent projects I've been part of, mainly looking at the space applications of robotics and the relation connecting robots and maths, or the equation, the scary equations. So I have had the chance to work on a range of space systems, starting with the launch vehicles or the rockets. So as a student, I was challenged with the task of modeling a launch vehicle. Trying to understand its complex dynamics was really hard, but I really enjoyed the maths that helped me understand how a launch vehicle would behave once it lifts off from the ground. So this was a very interesting project I worked with at the Indian Space Research Organization. Thereafter, I had the opportunity to work on modeling of satellites, modeling of robots, again looking at planetary exploration rovers as well as robotic manipulators for a range of in-space operations. So today I'm going to touch upon very briefly on different projects covering all these applications for space. And I will also show you some very interesting spin-out applications to the medical sector. Again, the focus will be on the mathematics that drives the systems that you're seeing on the screen. So we will not go into the details of any mathematical derivations, but I want to give you a flavor of how mathematical modeling plays a crucial role in defining the behavior or the performance of a robot, and how it helps engineers to actually analyze the real-life operation of systems, starting from simulation all the way to prototyping and field testing. So let's start with one of the hot topics, which is about designing robots for in-space operations, looking at how we can construct different structures in space, such as the International Space Station, or the future applications focused on constructing and assembling large aperture space telescopes. Similarly, there's a lot of opportunity looking at how robots, intelligent robots, can be used for servicing satellites in space, how we can use such robots for capturing space debris, how we can actually carry out in situ resources utilization beyond the Earth orbit, that is looking at asteroid mining and similar applications. So I'm going to give you a quick insight into how we actually tackle this complex problem of designing robots for in-space applications, targeting these missions. Okay, so let me start with one of the ongoing projects, which is actually led by my PhD student, Manu Nair. So Manu is actually working on a very interesting project, which is looking at how we can design an Antover ant walking robot for constructing the large aperture space telescopes. So this is about designing and operating space telescopes, not only for astronomical observation, but also for Earth observation. So we want to have such capable platforms in space, which will provide us useful data for improving the quality of lives on Earth. But the challenge for engineers is about how we go ahead with designing such capable robots. So one of the fundamental questions, or the mathematics, underlying mathematics, is about knowing the kinematics and the dynamics of these evokers. So we start with simple mathematics. So for example, what you see on this screen is a 5-degree freedom robotic manipulator, which is capable of walking on the surface of a spacecraft, as you can see in the rendering. So we can use very simple trigonometrical formulations to understand and define or derive the kinematical modulation formulation of this robot. Similarly, we use second order differential equations to capture the dynamics, the changing dynamics of this robot, which obviously depend on number of system parameters, such as its inertia, its Coriolis and gravitational effects based on what gravity conditions it's operating, and also on the centrifugal effects. So we use different ways of modeling to understand the kinematical and the dynamic formulations. And in this particular case, the robot is actually capable of walking. So when I say walking, in effect, this is a robotic arm, but it can latch on to different connector points on the surface of the spacecraft, and it can grab the telescopic mirrors, and it can further walk around and put the telescopic mirrors in the correct position on the telescope's truss. So this is a very complex operation that requires careful planning, careful execution, and we use mathematical models to understand how this robot will behave under the extreme conditions of space. So we use these equations as a starting point to simulate the behavior of this robot before even we can think of designing or prototyping it. So it's really important to derive an accurate model that can capture the behavior of the system. In this context, it's an evoker. And we then try to analyze how the system will change as we change the operating conditions. So these models plays a very vital role in helping us design the underlying control system that can then help to move the robot around to execute the task as needed. So it really shows that the starting point for engineers or space engineers working on complex missions like this is to really understand the underlying maths that defines the kinematics and the dynamics of a robot. Similarly, if you look at other examples or other mission scenarios where we can use space robots for servicing of satellites. Say, for example, we can extend the lifetime of an operational satellite by undertaking some maintenance work, some repair operations such as refueling. So even for these type of operations, we need space robots with some robotic capability. So when I say robotic capability, this is about, say, for example, having a robotic arm with a suitable gripper or a hand that can capture or dock with a client satellite and undertake the servicing operations. So here again, the underlying math is really complex. What you see on the screen is just a nutshell. But the reality is that when you start looking at the operation of a space robot under low gravity conditions or under earth analog conditions, it is very challenging. And we often start with defining the model of a satellite, which is very well established in the literature. So is the case with the model of a robotic arm for terrestrial applications. However, in the case of space applications, there are not accurate models yet, and therefore people tend to work on the assumption that, well, if your model is not very accurate, one way to tackle it is to look at how we can design robust controllers that can help with overcoming any shortcomings in the model of the system itself. So we do use both techniques. One is really looking at how precisely you can capture the behavior, the kinematical and the dynamic properties of your system in the form of a mathematical formulation. The second approach is, okay, you go with a nearly accurate system, need not be a 100% accurate model, but then you look at and how you can protect the system from misbehaving through designing a clever or a robust controller that can cope with the changing conditions of the space environment. So here, the way we approach this problem was to look at the intercoupling effects between a satellite and the robot. So for example, when you try to actuate the robotic arm to undertake any operation, this actually changes the attitude and position of the base spacecraft to which your robotic arm is attached. So this is a big problem. You can never ensure that you will be able to capture the target without any kind of collision unless you have a dedicated attitude control system for not only controlling the base spacecraft, but also a dedicated controller that can actually counter effect or nullify the effect of this coupling effect between the robotic arm and the base spacecraft. And these dynamical coupling effects are really difficult to capture using simple linear models, which are often used by researchers. So what we did was to really go into the depth of understanding the modeling of a complex space robot. And we started looking at how to capture this in its best way using nonlinear models. So the models you see on the screen are actually nonlinear models, which takes into effect all the coupling effect between the base spacecraft and the manipulator. And when we use a fully nonlinear model, it's also important to make sure that we use or we design a nonlinear controller that can understand the different nonlinearities inherent in the system. Therefore, the approach we used was to capture the model of a space robot using its nonlinear model, or in effect a full model that captures all the inherent nonlinearities. And then we designed a nonlinear controller that can then communicate with the model of the spacecraft, collect data from the onboard sensors, and generate the desired commands for actuating the robot. So this is one approach we are following, which we believe is one of the best approaches, considering that if you design a linear controller for a highly complex nonlinear system, the system need not be performing as expected. So there is always a risk of using linear controllers such as the classical PID, or the proportional integral derivative control, for controlling a complex nonlinear system like a space robot. So this is one approach, and you can find more details about the mathematical modeling, the control system design using H-infinity, and adaptive H-infinity in the publications by my student who already graduated. So Dr. Siddique's publications will give you more insight into how she tackled the problem of modeling a complex space robot and how to design a robust controller for servicing operations in space. Moving forward, there's also an interest in looking at how small a space robot can be. And another student I supervised at the University of Surrey, Lucy, she's actually looking at this very interesting problem of how small you can get when it comes to designing a space robot. And she also started looking at the modeling of a space robot based on the design she started off, which was a CubeSat based design. And she did an extensive trade-off on the sizing of the base spacecraft, starting with a 3U platform ranging all the way up to 24U. So here again, as you can see from the illustrations, this is all about understanding the complex dynamics and the kinematics that regulates the behavior of a system. And when it comes to space robots, it's often challenging because you don't have a fixed reference frame, because these are spacecraft that are operating or orbiting in space. And therefore, often we try to develop models with respect to the inertial reference frame, which is the reference frame attached to the center of the Earth. So this is one of the issues we have when it comes to modeling or deriving the mathematical models of a space robot for low Earth orbit as well as for other high Earth orbit applications. So here again, as you can see from the equations, we need to understand the inertial properties of the system. We need to understand the coupling effect between the base spacecraft and the robotic manipulator. We also need to understand the inertial properties of the robotic manipulator, and alongside with other nonlinearities such as the Coriolis and the centrifugal effects. Here for space applications, often we can simplify the model considering that the effect of gravity is minimal. And therefore, in some of our models, you wouldn't see the effect of gravity, whereas for any Earth-based testing, we will have to account for the effect of gravity, which adds more complexity to the nonlinearity of the system. So the idea of designing a small space robot is to really see whether we can have multiple systems operating in a cooperative way for future space missions. Because these small space robots, they can be designed in such a way that they can reconfigure in space, say for example, transforming from a single base satellite with a single arm into a larger space robot with dual arm capabilities. Or they could also, work as a group of multi agents trying to share the task when it comes to different assembly operations or servicing operations. So based on these mathematical models, we often start off with simulating the behavior of these robots, trying to understand, say, for example, what are the torque requirements? Because when it comes to space missions, it's often challenging to find actuators that are space qualified. When I say actuators in the context of manipulator, we are referring to DC motors, brushless DC motors. So it's often the question of whether we can get the desired performance with the currently available space qualified actuators. So these are all the extensive simulation-based studies we carry out based on the mathematical models of different space robots. Similarly, if you look at going beyond the Earth orbit, say for example, there is a lot of interest in asteroid mining missions. So we look at how we can design robots that can be used for asteroid mining operations. So another student of mine who is now continuing at University of Surrey, she started off looking at designing a self-reconfigurable undulating grasper or a snug robot, which is actually inspired by the way a python would capture its prey. At the same time, this is also taking into consideration that you do not want to damage or contaminate your sample that you're trying to collect from the asteroid. So this is about creating a virtual caging around your target. So independent of the size and shape of your target object, Snug can actually create a virtual caging around. And this caging will help to capture the target, but without crushing it or without deforming it. So this is another very interesting concept of a self-reconfigurable robot for asteroid mining operation. Here again, if you look at the maths, it's really complex. What I am showing the screen is just a snapshot, because when we started off with designing Snug, our challenge was how do we actually capture the behavior of this robot, especially the caging effect. You need to simulate, you need to understand the caging properties of this system. And this means we had to really go into the details of understanding the sizing of the individual modules of this robot. And then we started looking at initially the kinematical formulations, and gradually we moved on to the formulating the dynamical behavior. So together with the kinematical modeling and the dynamical models that we now have, we are now able to understand how to actuate Snug for different sizes of the targets. And based on this, we can also come up with some very intuitive ways of capturing the target. Say, this is actually an innovative aspect of this research, because if you look at how we can capture a piece of rock, say for example, on an asteroid, using a conventional rigid manipulator that you saw in the previous slides, it is very challenging. In effect, this is like trying to capture a fly using your chopstick. And this is not going to happen if you really want to do extensive in situ resource exploitation on asteroids. Therefore, it's really important to make sure that you are able to capture your target in the best way it can. And therefore, the concept of reconfigurable robots becomes more promising compared to the traditional rigid robotic manipulators. And here again, there is a lot of extensive maths that helps us in simulating the behavior of these robots. And based on these simulation results, Susanna is now into the next phase of her research where she is actually prototyping the design. Or in other words, she's converting the engineering models, the designs into a physical prototype that she can actually test under an earth and law condition. So here again, you will see more results in the publications and the underlying maths. Although it is complex, it is one of the most critical elements or critical component that helps us engineers to understand the behavior of these robots under unforeseen conditions. So this is another interesting project that I'm part of. Moving forward from in-space applications or in-orbit applications to planetary applications. So here again, I have had the chance to work with several researchers who worked on designing walking robots and wheel robots for planetary exploration. So if you start with a very simple rover, as you can see on the screen, the die-wheel rover, although I call it a simple rover, its mathematics or its behavior, the dynamics is really complex. But one simple approach to understand the behavior of a die-wheel rover that was developed by John, it's to really look at the mathematics of inverted pendulum. So we do learn about pendulum in our physics lessons at high school. And now we look at the behavior of inverted pendulum. So with this type of die-wheel rover, the dynamics is very similar to that of an inverted pendulum. So the challenge we had in designing the controller was to really convert or transform that knowledge into the model of a mobile die-wheel rover that is fully controllable using a classical PID controller. Obviously, you can develop other type of control systems as well, but this was a simple start to understand the complex behaviors of a die-wheel rover. Similarly, when you look at the walking robots, they also behave quite differently based on the type of the terrain, whether they're walking on a firm surface such as indoor lab conditions, or whether you take it out to the field where it might be walking over rocks or it might be walking over soft sand. Accordingly, the behavior changes. So some of my researchers, they looked at the detailed modeling of a single leg. Say, rather than designing a walking rover, we started off by understanding the complex dynamics of a single leg. So we started looking at how a single leg would interact with different types of planetary soils. So what you see here on the screen on the right side with a single leg test rig was an experiment that looked at how a walking rover would behave on a planetary soil simulant. So we knew the properties, the characteristics of the soil that we are using. And then based on the design of the leg, we were able to interpret how far, say, for example, the leg could sink, what will be the slippage if you change the soil into finer soils. And obviously, we also did extensive field testing to understand how their behavior will change under other operating conditions. So here again, we had a series of projects that explored several aspects of the behavior of walking robots, which looked at a range of biologically inspired systems, starting from spider all the way to stick insect. And also we looked at starfish inspired echinoderm robots. So a whole range of walking robot designs that helped us in understanding their behavior. But the most critical point I want to stress here is often we start off by analyzing the maths behind a single leg And then we move on into designing the full mathematical model of the full system based on whether it has 6 legs or 8 legs or 4 legs, or whether it's die-wheeled or whether it has 4 wheels or 6 wheels. Accordingly, the models evolve. But the starting point is basically similar. Similarly, we also worked on another concept, which is about a hybrid wheel-leg concept. This was another interesting project that was funded by the European Commission. Here again, we looked at the complex behavior that decides how a wheel or a wheel-legged system will change as you move, or as the rover moves over different planetary soils. And there was some extensive mathematical modeling involved in understanding or formulating this behavior, what you see on the screen. And we have several publications on this. You're very welcome to contact me if you're interested to read about the details of the mathematics. Unfortunately, we don't have the time to go into the details today, but I'll be happy to share some details offline. Also, it's important to stress that mathematics plays a vital role when it comes to understanding the soil properties, or when we try to look at, or when we try to understand how soil particles behave. There again, there is a lot of interesting correlation between the size of the particles as well as the corresponding physical properties of the soil. So here again, we use some numerical modeling techniques for formulating the empirical models that then helps us in understanding the soil characteristics. So we were part of a study from the European Space Agency and Airbus, which helped us in undertaking some extensive experimental research that helped us in formulating the characteristics of different planetary soil simulants. So here again, there's a lot of mathematics involved, even when we try to understand the particle size of a planetary soil. So another interesting topic of research. Moving into some of the technology transfer applications from space robotics to medical robotics, this is another very exciting topic where we cannot live without maths. So, for example, when you hear about soft robots, these are often inspired by nature. And one of our projects that I was part of, this was really looking at how we can design a flexible or soft medical robots that are inspired by octopus. So octopus is a wonderful creature that has a capability to squeeze through narrow openings. So similarly, as engineers, we were curious to explore whether we can design a flexible soft medical robots that can squeeze through the narrow openings of the trocar port when it comes to robotic surgery. So this was what actually inspired us to work on the Stiflop robot, which was a European Union funded program. When it comes to modeling and controlling a soft robot, it's much more complex than modeling and controlling a rigid industrial robot. And this is because these soft robots are continuum robots, and their behavior changes based on the materials we use, based on the type of actuation systems that we use, and depending upon whether you have sensors embedded with the system or not. Accordingly, the way we control the system changes. So often in the case of soft robots, one of the standard approaches we use for modeling soft robots is to really understand the stiffness properties of this robot. And this in turn depends on the material we use for designing the robot. And one of the standard approaches is actually to develop the stiffness metrics of this robot, as you can see on the screen, using the Euler-Bernoulli beam theory model and using Hooke's law. So once you know this mathematical formulation that helps us with understanding the stiffness properties of the system, you can actually design your controller to regulate the way the robot changes its stiffness. So it can become hard or it can become soft, and you can do this in a controlled fashion based on the various sensor data you get, such as from the force sensors, the tactile sensors, the pressure sensors, the position sensors, and so forth. So here again, we have several interesting publications, which I will be happy to share with an interested audience. To conclude the topic on soft medical robots, I would like to emphasize that this is a very interesting field of research where mathematics plays a very crucial role. And without understanding the underlying maths, it is very difficult to design a physical system that will operate the way we expect to do, especially when it comes to surgical operations or surgical procedures. Health and safety is really important. So you want to make sure that you can deliver a product or a system or a tool that will be safe to operate on patients. And therefore, as engineers, we try to carry out extensive mathematical modeling to refine the design, and we work collaboratively with computer scientists to also understand how we can induce intelligence into these man-made robots. So it's a very, I would say, multidisciplinary effort because it's not just engineers who design robots. We are good at designing the robots, but we also collaborate with computer science experts who can actually support us in creating a system that is as intelligent or more intelligent than humans. So with this, I'm actually approaching the concluding part of my talk. So I started off with the importance of mathematical modeling for space robots. Then you saw how some of those know-how can be transferred to the medical robotics industry, where soft robots are becoming an important element. Now we are also applying this soft robotic technology for the agri-robotics research at the University of Lincoln. So some of my colleagues from School of Engineering are developing flexible grippers. Similarly, my colleagues at the Lincoln Institute for Agri-Food Technology, they are actually working on a range of robotic platforms, wheeled systems that are used for harvesting soft fruits. So when it comes to robots and its application for the agri industry or agri-food industry in a broader sense, there is a lot of interesting maths, hidden maths, that actually helps us in understanding the behavior of these systems under dynamic operational conditions. And that is what actually helps us in designing precise controllers that helps us in effective, in developing effective systems. So with that, I would like to conclude my talk by stressing the fact that mathematics is actually in the DNA of robots. So it is impossible to design a robot without going through its mathematical formulation. I know it is crazy, it looks crazy, it looks complex, but we engineers, we love maths, and as engineers, we very well enjoy the mathematical formulation that helps us designing innovative robots for numerous applications. So with that, I would like to conclude my talk today. You're very welcome to contact me via email if you're interested in reading any of the publications that I showed you today. And I would take this opportunity to also invite you to attend a workshop that University of Lincoln is co-organizing with other universities and institutions from the US. So this is about robotic in-situ manufacturing, structural assembly and servicing for space. And you can find more details from the corresponding website. So with that, I'm concluding my talk. I'm happy to take up any questions from the audience, and feel free to pop over with all your questions. Thank you.
Well, thank you very much, Mini, for a fascinating view about the many applications of robots, and of course, within those applications, the applications of mathematics as well. There are some questions queuing up in the Q&A box, but I'd like to take the chairman's privilege of asking the first one myself, if I may. It's about the interaction of your projects with mathematics. You already said that you work with mathematicians and computer scientists and other disciplines, and of course the application domains. Could I ask, when you find that you need mathematics to express or to model the behavior of your robots, is that mathematics there, as it were, to hand, just waiting for you to use, or are there new challenges to mathematics and mathematicians arising out of your work?
There are some existing literature on modeling of standard robotic platforms. Okay, so there are plenty of textbooks, and we do teach undergraduate students about the basics of modeling. But when it comes to research projects where you deal with more complex systems, often you don't have everything well defined. And therefore, it is not always easy for us to start off with something that exists. So we start off with a piece of paper and a pencil. We start deriving, we in fact start with a sketch. So as engineers, we like to start sketching our system first. And then we try to discuss or try to understand its model. Or in other words, if I'm dealing with a robotic manipulator, I look at how to capture its motion. If I'm dealing with a ground vehicle, I'll try to understand whether it's a wheel system, whether it is using other type of locomotion system, where we are going to operate, what are the different ways it would interact with the terrain. Accordingly, our approaches actually varies. So no standard models actually exist, and we often start from scratch with some basic understanding of how things were done in the past when we look at designing complex systems for future applications.
Thank you. That all sounds very exciting, and in fact that brings me on to one of the questions in the Q&A box. Michael asks, are your robots actually in use at the moment? And if they are or will be used, you mentioned asteroids. Will your robots be exploring Mars or the Moon?
Yeah, it's a very long journey. I must admit that space missions in particular, they could easily take years or decades. So we are very much hopeful that we will be able to fly our robots in future missions. But as of today, particularly if you look at the asteroid mining, it is a R&D activity that's under development. So we are in the phase of prototyping the SNUG robot. Similarly, with our wheeled planetary rovers, we have done extensive field work. The data was used by our industrial partners who are part of the European Space Agency's ExoMars mission. So indirectly, we are able to feed into actual missions. Although as academic institutions, we don't always have the privilege of flying things, we do have the opportunity to collaborate with industries and space agencies, thereby feeding in the data or the resource that helps them to refine the robots they are going to fly. So it's a difficult route, but often we do have the chance to engage with space agencies and industries who are directly part of missions.
Thank you. There are two more questions which I'll take together, or at least I think they go together. One from Michael, who asked about the SNUG robot, details of the parameters in the equations and how they related to its structure. And I think that might be the similar question to one from William, who says, are robots modeled using topological dynamics?
It depends. In the case of SNUG, obviously, we started off with a modular approach. So based on the extent of modularity in its design, accordingly, the type of parameters that we choose for tuning will change. And in the case of SNUG, we do have certain parameters that we have to select carefully. For example, you might recollect in my slide, there were two parameters, alpha and beta, I guess. And these are two critical parameters, because if the values of these two parameters are smaller, that ensures that the diameter of the encircling can be larger. Or in other words, you have a more smooth enclosure around your target. So there are a number of design parameters that we need to tailor in order to get the desired performance. The details of the tuning process can be found in one of our publications, which I'm happy to share later.
Thank you. I'll just take one more question from the box, since we're about to run out of time. I think what Michael again asked about the advantages of legs rather than wheels on robots. Could you just say a word or two about what the difference is?
Sure. The most successful Martian rovers have been wheel rovers. Okay, so it's proven, it's a space qualified design. Whereas these wheel rovers do have the challenge of traversing on steep terrain. They cannot actually explore craters or crevasses. And this is why there is a need for other mobility systems like legged systems, which can easily climb over such steep terrains, or explore more challenging uneven terrains, which unfortunately the current wheel systems cannot.
And I guess they have the advantage, if that's the right word, of posing new and interesting challenges to the engineers and the mathematicians involved.
Absolutely.
Thank you. Thank you. I think that's a very good note on which to end our Q&A session. Firstly, of course, I'd like to thank you, Mini, for a fascinating talk in which you've shown how your work and the mathematics that contained within it ranges from the reaches of outer space to the inside of the human body, which is a fascinating range of environments and of challenges, both physical and mathematical. And I would like to thank you once again for a fascinating contribution to our Mathematics 2020 lecture. Thank you very much.
Thank you, Richard, and thanks for this invitation. Thank you. Bye.